the probability of tunneling is given by T equals G times E raised to the minus 2 KL, where G equals 16 E over U naught times 1 minus E over U naught, where E is the energy of the particle, U naught is the potential of the barrier, and K, as we've seen before, is the square root of 2m U naught minus E all over H bar. So it might be useful to find what G and K are before we do parts A and B. So G equals 16 times 2 electron volts over 5 electron volts times 1 minus 2 electron volts over 5 electron volts, which gives us a value of 3.8, and K is going to equal square root of 2 times 9.11 10 to the negative 31st kilogram times 5 EV minus 2 EV, and then this we need to change to joules, so this would be 1.6 times 10 to the negative 19 joules per EV all over H, which is 1.055 times 10 to the negative 34 joules second. And if we do that, we get 8.9 times 10 to the 9th per meter. And now we can say that for part A, which we know L is 1.0010 to the negative 9 meters, that means that 2KL is going to equal 2 times 8.9 10 to the minus 9 meter inverse times 1.00 times 10 to the minus 9th meter, which is 17.8. That means that T equals 3.8, which is RG times E to the minus 17.8, which is 7.1 times 10 to the minus 8. So that's about point that much. So very small number. And then part B, now L equals 0.5 times 10 to the minus 9, which means that T equals 3.8 times E to the minus 2 times 8.9 10 to the minus 9 per meter times 0.5 10 to the minus 9 meters, which would equal 5.2 times 10 to the minus 4, which is 0.00052. So as the wavelength as the length decreases, the probability of tunneling will increase, and therefore we can say that the tunneling is very sensitive to the width of